topic 8, it's really important that you know what all of these formulas mean and what each of the symbols are. Spend some time learning all these symbols because quite often you have to use these formulas. So the first one, the Sankey diagram of a fossil fuel power station is shown below. Now we know our Sankey diagram is basically just gives us a distribution of where the energy goes, and you should know this for a fossil fuel. You're looking for an oil-based or a coal-based, natural gas-based power station. So which of the following best identifies the thermal energy removed by water and the electrical energy output? Now this over here would be our output. Usually in a Sankey diagram, all of these are showing when they're pointing down like these are all losses of energy. So one definitely is used for output. So we're looking at one, either this over here, A or C. And then removed by water, because all these fossil fueled power stations basically heat up water into a gas, into steam, and use that to drive a turbine. There is a lot of energy loss in that. That's where your major energy loss goes. So we have our thermal energy removed in 2. So that would be answer A for question 25. Here we have world energy resources include coal, nuclear fuel, and geothermal energy. Which of the following lists the resources in order of energy use in the world? So hopefully you would know that coal is your major one, so it would be either this and this, and then nuclear, then geothermal, so it would be D. So that's a straight knowledge-based question. One that you need to have that background knowledge to be able to do. Going on to 27, it says which of the following processes leads to the production of a nucleus of plutonium-239 from a nucleus of uranium-238. So in looking at you realize, I hope, that the 239 is giving you your atomic mass number. It's basically the number of protons and neutrons. So we see here that we are increasing our we are increasing our number of protons and our number of neutrons. So in here we need to look at something which would increase that. You see, it's going from uranium-238 plus something, whatever it is, to the plutonium. I've forgotten what the symbol for plutonium is. Well, let's just call it PL. That's 239. So you can see that this has increased. So what would do that? Well, neutron capture would be good. That would definitely lead to an increase in your atomic number, your atomic mass number. Radioactive decay. Now that's decay, so that's giving off particles. So you would expect your atomic mass number, your nuclear number, to decrease. So that wouldn't be. Electron capture by a uranium nucleus. Now that could increase your number of neutrons, but here it wouldn't increase the total number of nucleons. That would remain the same. And nuclear fission, that's when you split up. So it's definitely going to be A, is correct. Here we have 28. Water is contained in a tidal basin behind a dam. The water has a depth h at high tide and 0 at low tide, as shown in the diagram. The gravitational potential energy of the water shared in the basin between the high tide and the low tide is proportional to what? Sorry, not shared, but stored. So the gravitational potential energy of the water stored in the basin between high tide and low tide is proportional to what? Well, we know that our gravitational potential energy EP is equal to mgh. So it certainly is proportional with the h. So we'll be thinking that this one, but hang on a moment with this, because it's also to do with the mass. Now, your mass is obviously going to be related to your volume, because you have your density is equal to mass over volume. So mass is equal to your density times volume, and your volume is a height dependent. If we say this is your surface area here, then your volume is equal to that area times by height. So you're going to get your density times your area times your height. So if I put this into my EP formula, that's going to be your density times your area times your height times g times height. So you're going to have a height squared term here. So that is why C, 28C would be the correct answer. And our last two questions here. We have surface X has a temperature of Tx and an emissivity of epsilon E. I'm actually just going to make this slightly bigger because I'm having a bit of a problem reading this off the board. So let's just make this a bit bigger. There we go. Alright, that's better. So we have surface X has a temperature of Tx and an emissivity Ex, and surface Y has a temperature of Ty and an emissivity of this epsilon y or little e y. The two surfaces emit radiation at the same rate, so that would be your power amount, is your energy per unit time. What is the ratio of that? Now, we would need to use one of these formulas over here. Would you need to use this formula over here, that your power is equal to your emissivity times your, this is Boltzmann's constant, times your area times your temperature. So we can put this down for power for X. Now we want the Tx over Ty. So let's do it like this. Power for X is going to be your X sigma, which is a constant, your area, and your Tx to the 4. And we're going to divide that by your power for Y. It's equals to emissivity Y, sigma area T to the Y to the 4. Now, it says the two surfaces emit radiation at the same rate, and so we would expect here that your area and your sigma are all going to be the same, and your Py and Px are going to be the same. So that would be 1 is equal to this, and so I'm going to cross multiply over here. This would be your emissivity Y over emissivity X is equal to Tx to the 4 over Ty to the 4. Obviously I do this to the quarter, I do this to the quarter to get rid of those, and I am going to get A for this one, 29A. I think you can see it there. Okay, so again, identifying your formula, really important. Knowing that when it says that the radiation emits radiation at the same rate, that we're talking about power, is important also. And our final question for this paper. It says large areas of rainforests are cut down and burned every year. The result of these actions is, now a reduced albedo. It's not actually reduced, it actually increases the albedo in some cases, because forests being quite dark actually absorb quite a lot, so that's not correct. Reduce carbon fixation, this is correct, because your rainforests, your forests are changing carbon dioxide. They take in carbon dioxide, they form your carbon molecules within the plants, and they give off oxygen. So this gets put into plant material and it gives out oxygen. Increased evaporation rate, no, that is not. You'd actually decrease that because you get a lot of moisture being formed there and a lot of transpiration and evaporation. And increased mass of atmospheric methane, also not correct. So B is correct there.